Hello all, welcome to this video on probability and distributions. Today I'll be talking about Gaussian distribution and introduction to conjugacy and exponential family. Let's begin. The Gaussian distribution is the most well-studied probability distribution for continuous valued random variables. It is also referred to as the normal distribution. Its importance originates from the fact that it has many computationally convenient properties. There are many other areas of machine learning that also benefit from using a Gaussian distribution. For example, Gaussian processes, variational inference, and reinforcement learning. It is also widely used in other application areas such as statistics for hypothesis testing, signal processing for Kalman filters, and control for linear quadratic regulators. For a univariate random variable, the Gaussian distribution has a density that is given by P of x given mu, comma sigma square, which is equal to 1 by root of 2 pi sigma square, exponential of minus x minus mu the whole square by 2 sigma square. The multivariate Gaussian distribution is fully characterized by a mean vector and a covariance matrix, which are mu and sigma respectively, and defined as P of x given mu, comma sigma, which is 2 pi the whole raised to minus d by 2, mod of sigma the whole raised to minus 1 by 2, exponential of minus half x minus mu the whole transpose, sigma inverse x minus mu, where x belongs to the d dimension space. So we'll write P of x as a normal distribution with mean x given mu and variance sigma, or in this way. Here we have three figures. This one is a univariate one-dimensional Gaussian. So here the red cross is showing us the mean and the red line will show us the extent of variance. This is a multivariate, that is two-dimensional Gaussian, that is viewed from the top. The red cross shows the mean and the colored lines show the contour lines of the density. And this is the figure of a Gaussian distribution of two random variables x1 and x2. So the standard normal distribution will be a special case where the mean will be 0 and sigma will be an identity matrix. Gaussians are widely used in statistical estimation and machine learning as they have closed form expressions for marginal and conditional distributions. A major advantage of modeling with Gaussian random variables is that variable transformations are often not needed. Since the Gaussian distribution is fully specified by its mean and covariance, we can often obtain the transform distribution by applying the transformation to the mean and covariance of the random variable. Now we'll see that both the marginals and conditionals of Gaussians are Gaussians. For this, we'll take x and y, which are two multivariate random variables that may have different dimensions. To consider the effect of applying the sum rule of probability and the effect of conditioning, we explicitly write the Gaussian distribution in terms of the concatenated states x, y. Now P of x, y can be written as a normal distribution with means mu x, mu y, and covariance matrices sigma xx, sigma xy, sigma yx, and sigma yy, where sigma xx is the covariance of x, x, and sigma yy the covariance of y, y, which are the marginal covariance matrices of x and y respectively, and sigma xy is covariance of x, y, which is the cross covariance matrix between x and y. The conditional distribution P of x given y is also Gaussian and is given by P of x given y which is a normal distribution with mean mu x given y and variance sigma x given y, where mu x given y can be written as mu x plus sigma xy, sigma yy inverse into y minus mu y. And sigma x given y can be written as sigma xx minus sigma xy, sigma yy inverse into sigma yx. Note that in the computation of the mean here, the y value is an observation and no longer a random. The marginal distribution P of x of a joint Gaussian distribution P of x comma y is itself Gaussian and computed by applying the sum rule, which is given by P of x, which is an integral of P of x comma y dy, which is a normal distribution with mean x given mu x and covariance matrix sigma xx. Now we'll consider a bivariate Gaussian distribution, which is given by this figure here, which is denoted as P of x1 comma x2, which is a normal distribution with its mean values 0, 2 and the covariance matrices with values 0.3, -1, -1 and 5. This is a marginal distribution. So we saw that the marginal of a joint Gaussian distribution is Gaussian, and this is a conditional distribution, which is also a Gaussian. We can compute the parameters of the univariate Gaussian, which is conditioned at the value x2 is equal to -1, by applying the previous equations to obtain the mean and variance respectively. So that will be mu of x1 given x2 is equal to -1. On substituting the values in the previous equation, we get 0 plus -1 into 0.2 into -1 -2, which is 0.6. And sigma square of x1 when given x2 as -1, 0.3 minus -1 into 0.2 into -1, which is 0.1. Therefore, the conditional Gaussian is given by P of x1 given x2 is equal to -1, which is a normal distribution with mean 0.6 and variance 0.1. The marginal distribution P of x1, in contrast, can be obtained by applying the same, which is essentially using the mean and covariance of the random variable x1, which is already given, which will give us P of x1 as a normal distribution with mean as 0 and variance as 0.3. Now we look into the product of Gaussian densities. We apply the Bayes theorem to compute the posterior, which results in a multiplication of likelihood and the prior, that is the multiplication of two Gaussian densities. We have discussed the computation of posterior in one of the previous videos. Now the product of two Gaussians, which is a normal distribution with mean x given a, comma a, and another distribution x given b, comma b, is a Gaussian distribution that is scaled by a constant c, which is a real number given by c into a normal distribution where mean is x given c, comma c, with c is equal to a inverse plus b inverse, the whole inverse. This can be rewritten as c is equal to c into a inverse a plus b inverse b. On substituting the values, we get the final equation as c is equal to 2 pi the whole raised to minus d by 2, a plus b, whose mod value raised to minus 1 by 2, exponential of minus 1 by 2, a minus b transpose, a plus b inverse into a minus b. Now the scaling constant c itself can be written in the form of a Gaussian density either in a or b with an inflated covariance matrix a plus b. That is, c is equal to a normal distribution where mean is a given b and variance is a plus b, which is also equivalent to a normal distribution with mean b given a and variance as a plus b. Now we look into sums and linear transformations. If x, y are independent Gaussian random variables, that is the joint distribution is given by p of x comma y, which is p of x into p of y, with p of x as a normal distribution where mean is x given mu x, variance is sigma x, and P of y being a normal distribution where mean is y given mu y and variance is sigma y, then x plus y is also Gaussian distributed and is given by P of x plus y, which is a normal distribution with mean mu x plus mu y and variance sigma x plus sigma y, which is just adding the corresponding means and the variances of x and y. Knowing that P of x plus y is Gaussian, then the mean and covariance metrics can be determined immediately using the results we saw before. Since expectations are linear operations, we can obtain the weighted sum of independent Gaussian random variables as P of ax plus by, which is a normal distribution where mean is a into mu x plus b into mu y and variance is a square mu x plus b square mu y. Now let us consider a mixture of two univariate Gaussian densities. P of x given by alpha p1 of x plus 1 minus alpha p2 of x, where the scalar alpha is in the range 0 to 1, which is the mixture weight. P1 of x and P2 of x are the univariate Gaussian densities with different parameters, that is mu1 sigma 1 square not equal to mu2 sigma 2 square. Then the mean of the mixture density P of x is given by the weighted sum of the means of each random variable, that is expectation of x equal to alpha mu1 plus 1 minus alpha mu2. And the variance of mixture density P of x is given by V of x, which is alpha sigma 1 square plus 1 minus alpha sigma 2 squared plus alpha mu1 squared plus 1 minus alpha mu2 squared minus alpha mu1 plus 1 minus alpha mu2 the whole squared. For a mixture density, the individual components can be considered to be conditional distributions, that is conditioned on the component identity. The equation that we got before is known as the law of total variance, which generally states that for two random variables x and y, it holds that Vx of x is equal to Ey of Vx of x given y plus Vy of Ex of x given y. That is, the total variance of x is the expected conditional variance plus the variance of the conditional mean. In the following equation, we will see that there is a bivariate standard Gaussian random variable x and we perform a linear transformation Ax on it. The outcome is a Gaussian random variable with mean 0 and covariance A transpose. Observe that adding a constant vector will change the mean of the distribution without affecting its variance, that is, the random variable x plus mu is Gaussian with mean mu and identity covariance. Hence, any linear or affine transformation of a Gaussian random variable is Gaussian distributed. Now we'll consider a Gaussian distributed random variable x. It's a normal distribution where mean is mu and variance is sigma. For a given matrix A of appropriate shape, let y be the random variable such that y is equal to Ax, which is a transformed version of x. We can compute the mean of y by exploiting the fact that the expectation is a linear operator. So E of y will be E of Ax, taking out A into Ex, which is A mu. Similarly, the variance of y can be found as V of y, which is same as V of Ax. Now, taking out A, we will multiply it with A transpose, that is A into Vx into A transpose. Vx will be replaced by sigma, which is A sigma A transpose. This means that the random variable y is distributed according to P of y, which is a normal distribution with mean y given A mu and variance A sigma A transpose. Now let us consider the reverse transformation. When we know that a random variable has a mean, that is a linear transformation of another random variable. For a given full rank matrix A belonging to m cross n dimension space where m is greater than or equal to n, let y belong to the m dimension space, which is a Gaussian random variable with mean Ax. Then P of y is a normal distribution with mean y given Ax and variance sigma. If A is invertible, then we can write x is equal to A inverse y and apply the transformation. However, in general, A is not invertible and we use an approach that is similar to that of pseudo-inverse. That is, we'll pre-multiply both sides with A transpose and then we'll invert A transpose A, which is symmetric and positive definite, which will give us the relation y is equal to Ax, which is also equivalent to A transpose A inverse A transpose y equal to x. Here x is a linear transformation of y and we obtain P of x, which is a normal distribution with mean x given A transpose A, the whole inverse A transpose y, and variance A transpose A, the whole inverse A transpose sigma A transpose A, the whole inverse. Now we look into sampling from multivariate Gaussian distributions. In case of a multivariate Gaussian, the process will consist of 3 stages. The first is we need a source of pseudo-random numbers that provide a uniform sample in the interval 0, 1. Second, we use a non-linear transformation such as the Box-Muller transform to obtain the sample from a univariate Gaussian. And for the third step, we collate a vector of these samples to obtain a sample from a multivariate standard normal, which has mean 0 and identity matrix as its variance. Now, to obtain samples from a multivariate normal with mean mu and variance sigma, we can use the properties of linear transformation of a Gaussian random variable. That is, if x has a normal distribution with mean mu 0 and variance identity matrix, then y is equal to ax plus mu, where A transpose will be replaced by sigma, which is Gaussian distributed with mean mu and covariance matrix sigma. One convenient choice of A is to use Cholesky decomposition of the covariance matrix sigma, which is A transpose. The Cholesky decomposition has the benefit that A is triangular, leading to efficient computation. Now we look into the introduction on conjugacy and the exponential family. Many of the probability distributions that we find in statistics textbooks were discovered to model particular types of phenomena. For example, we have seen the Gaussian distribution. The distributions are also related to each other in complex ways. Beginning with it, it can be overwhelming to figure out which distribution to use. In addition, many of these distributions were discovered at a time that statistics and computation were done by pencil and paper. We previously saw that many of the operations required for inference can be conveniently calculated when the distribution is Gaussian. Now we look into some of the properties that are needed for manipulating probability distributions in the machine learning context. First property required is there is some closure property when applying the rules of probability, that is Bayes' theorem. By closure, we mean that applying a particular operation will return an object of the same type. Second property is as we collect more data, we need more parameters to describe the distribution. And the third property is since we are interested in learning from data, we want parameter estimation to behave nicely. It turns out that the class of distributions called the exponential family provides the right balance of generality while retaining favorable computation and inference properties. Now we look into three probability distributions: Bernoulli, binomial, and beta. We'll begin with Bernoulli. It is a distribution for single binary random variable x with state x, which is element of 0, 1. Now this is governed by a single continuous parameter mu, which is also belonging to 0, 1, that represents the probability of x is equal to 1. Now the Bernoulli distribution is defined as p of x given mu, which is mu raised to x into 1 minus mu the whole raised to 1 minus x, where x is an element of 0, 1. Expectation of x is mu, and variance of x is mu into 1 minus mu, where e of x and v of x are the mean and variance of the binary random variable x. An example where the Bernoulli distribution can be used is when we are interested in modeling the probability of heads when flipping a coin. Next is a binomial distribution, which is a generalization of the Bernoulli distribution to a distribution over integers. In particular, binomial can be used to describe the probability of observing m occurrences of x is equal to 1 in a set of n samples from a Bernoulli distribution where p of x equal to 1 is mu, which belongs to 0, 1. Now, a binomial distribution n comma mu is defined as p of m given n comma mu, n choose m, mu raised to m into 1 minus mu the whole raised to n minus m, where expectation of m is n mu and variance of m is n into mu into 1 minus mu. Now this is an example of binomial distribution for three values of mu, which are 0.1, 0.4 and 0.75 for n is equal to 15 experiments. An example where binomial could be used is if we want to describe the probability of observing m heads in n coin flip experiments, if the probability of observing heads in a single experiment is mu. Lastly, we have beta distribution. This is a distribution over a continuous random variable mu, which is an element of 0, 1, which is often used to represent the probability for some random binary event. For example, the parameter governing the Bernoulli distribution. Beta distribution itself is governed by two parameters, alpha and beta, which are greater than 0, and is defined by p of mu given alpha comma beta as tau of alpha plus beta by tau of alpha into tau of beta into mu raised to alpha minus 1 into 1 minus mu raised to beta minus 1, where expectation of mu is alpha by alpha plus beta and v of mu is alpha beta by alpha plus beta the whole square into alpha plus beta plus 1. Now here, tau is a gamma function that is defined as gamma of t, which is an integral from 0 to infinity x raised to t minus 1 exponential of minus x dx, where t is greater than 0, and tau of t plus 1 is t into tau of t. Note that the fraction of gamma functions we saw before normalizes the beta distribution. Intuitively, alpha moves probability mass toward 1 and beta moves probability mass towards 0. There are some special cases though. For alpha and beta both being 1, we obtain a uniform distribution u of 0, 1. For alpha and beta less than 1, we get a bimodal distribution with spikes at 0 and 1. For alpha and beta greater than 1, the distribution is unimodal. And for the case alpha and beta greater than 1 and alpha equal to beta, the distribution is unimodal, symmetric and centered in the interval 0, 1. That is, the mean or mode will be at 1 by 2. This is an example of beta distribution for different values of alpha and beta. That's all for now. Thank you for watching.